Okay, good morning and welcome to Lesson 8 of Module 6. Today we are going to be informally fitting a straight line, called a line of best fit, to displayed data that's in a scatter plot. You'll know you're successful when you can make predictions based on the graph of that line that has been fit to that data. Okay, we're going to go through some examples and exercises, and then we'll close out the lesson. You'll do an exit ticket and reflection. And then you'll have a little bit of time to work on your weekly work and any missing work. Let's go ahead and get started. All right, to begin with example 1, this is all about housing costs. So it says, let's look at some data from one Midwestern city that indicates the sizes and sale prices of various houses sold in the city. So the Bavariate data, the two variables are the sizes of these homes and the sale prices of these homes. Okay? So we have two side-by-side tables, each with the size and then the price listed beside it. And then it says, what can you tell about the price of large homes compared to the price of small homes? So what I'm going to do is I'm going to highlight the larger homes in green. So this one's 5,000 square feet. That's pretty high. 4,000, that's pretty big. Here's another 4,000 square foot home. Let's see, this 3,000 square foot home is pretty big too. So those are the larger homes here. I would even say anything that's a little bit over 2,000 square feet is a big house. So those are our larger homes, okay? And then I'm going to highlight the smaller homes in red. So that these are the ones that are under 1,000 square feet. Those are the tinier ones, and then here's one that's like right at 1,000. Right at 1,000. Okay, so let's look at these prices and make a conclusion about this data. So it says, what can you tell of the price of large homes compared to smaller homes? So this large home is $1 million. This one is almost 800,000. This one is 200,000, 224,000, but these ones are a lot less square feet, like honestly half the size, so maybe I won't look at those two. And then we have a 4,000 one, which is 650,000. This 3,600 square foot is 670,000, and again this one's like only 2,000 square feet. So I'm gonna look at these ones right here. So I have $800,000, almost $1 million for this home, 660 and 670. So those are really big prices. And then let's look at that and compare it to the smaller homes. And this smaller home is $60,000, so literally like $100,000 less than some of them, or sorry, $600,000 less than some of them. This one is like 150 around there, and less than $100,000. So the price of the larger homes compared to the price of the smaller homes is a lot greater. Just please write this down. The price of the larger homes is much greater than the price of the smaller homes, which is pretty, self-explanatory. You get a bigger house, you pay more money. You get a smaller house, you pay a lot less money. Now, what's nice is on the next screen, we're going to look at this data, same data, just in a scatter plot, and you'll see how much easier it is to kind of interpret it. Going through this table is a little bit difficult. Maybe if it was listed in order from like least to greatest, it would be easier. But when you look at a scatter plot, it is so much easier to observe the data and make predictions and make conclusions. So make sure you have this down, and we're going to go to the next slide. All right, so here is the data all put into a scatter plot. You can see that it is a lot easier to understand. And you can also probably see a trend here. It says, does the scatter plot seem to support the statement that larger houses tend to cost more? Well, here's the square feet down here. So here's the largest one. It's on this line. Does that cost the most? Yes, that's the highest cost. Here's the smallest house. Does that cost the least? Yes. So the scatter plot shows us and does support our conclusion that larger houses cost more. Okay, moving on to the next slide. This question asks us, what is the most expensive house and where is that on the scatter plot? That most expensive house was a little over, what, $1 million? And it is right there on the scatter plot, which lines up at a little over 5,000 square feet, a little over $1 million. Okay. And I'm not even going to write anything here. I'm just going to highlight it and show that on my graph. And I would say that that is definitely an outlier. You can see that that is way off on its own. There's not a lot of houses that are that expensive in this town, obviously. Most of them are a lot less expensive than that. Moving on. Okay, so here's where the prediction part comes into this lesson. It says some people might consider a given amount of money and then predict what size house they could buy. So some people might be like, okay, well, my budget is $150,000. How big could the house be that I'm going to get? Realistically, about how big is it going to be? And basically, this is asking us, how would we do that? How will we do that on this graph? Well, the first thing you have to do is you have to draw what is called a line of best fit. And we were doing this a little bit yesterday. But basically, you want to draw a line that pretty much goes through your points. And then from there, you can pretty say, okay, well, if I want to spend $300,000 right here, then if I draw this line and it hits my line of best fit, I'm going to get something that's a little bit over 2,000 square feet. Okay? And they would predict that because they would predict, oh, well, there's probably going to be a spot there on my scatter plot. So how would you use this table to make a prediction? You would draw a line of best fit. And use it to predict. Okay. Make sure you have that down and we will move to the next screen. All right, based on that line of best fit, it wants us to estimate the cost of a 3,000 square foot house. So if I would draw this line of best fit again, and I go to my 3,000 size, and I draw it up until it hits my line of best fit. And then I connect it to my y-axis. This is right in between 400,000 and 600,000. I would say right around $500,000 for a 3,000 square foot home. Okay, and please draw those lines on the graph so that you can see how we did that, how we found that number. Moving on. So I kind of did this already, but it says draw a line in the plot that you think would fit the trend in the data. I'm going to draw mine there. Yours might be off a little bit, but basically it needs to pretty much hit most of those points or have them really close, as close as they can be. Okay, you don't want too many on top of it, too many below it, and you want it to kind of match the pattern that you see. And then we'll move on. All right, here it says use your line to answer the following questions. What's the price of a 3,000 square foot home? Right around 500K. And then what is the price of a 1,500 square foot home? So it's going to be right around here. That is about 200,000K. Okay, so I'm just showing you the practicality of how to use this line of best fit. Moving on. here we're just going to dive a little bit more into drawing those lines of best fit. It says, consider the following general strategies students use for drawing a line. Do you think they represent a good strategy for drawing a line that fits the data? Okay, so if we don't draw a good line, then our predictions are going to be off, right? It says, explain why or why not, or draw a line for the scatter plot using the strategy that would indicate why or why it is not a good strategy. So Lori thought she might draw a line, or draw her line, using the very first point and the very last point. So she said, okay, I'm going to go from this point right here to this point right here. And so her line is like that. Okay. Phil wants to be sure that he has the same number of points above and below the line. So his is a little bit more crazy. So right now above the line we have 1, 2, 3, 4, 5. Below we have 1, 2, 3, 4, 5, 6, 7, 8. So he would probably make his line, well, if we have 5 and 8, it's going to be a little bit harder. But he would probably make his line like that. Okay. Now there's 1, 2, 3, 4, 5, 6, 7 above, and 1, 2, 3, 4, 5, 6 below. It's about as much as you're going to be able to do, but that would be his line. Sandy thought she might try to get a line that had the most points right on it. So the line that would have the most points right on it would probably be this, because you would hit all of these. Okay, so that's Sandy. And then Marcy decided to get her line as close to as many of the points as possible. So she said, you know what, it's probably not going to be able to go through all of them, but I want it to be as close as possible to all of them. So hers would probably be right around there. Okay. Now all these are pretty good strategies for this graph because the trend is pretty clear. But I'm going to let you know the best strategy is this last one, Marie. I said Marcy before. This is the best strategy. And this is the one I want you to use because it's going to give you the most accurate predictions. This one with the most points on it, it's not always going to be correct because just because it has the most points in a straight line doesn't mean that's the line that fits the data. So if you look at this red line here, this line is kind of a lot lower, a lot less steep than it needs to be. Okay. Phil wants to be sure it has the same number of points. That's not something that has to happen because sometimes you're going to have a lot more on above the line than below, or vice versa, and that does not affect your trend at all. And then using the first and last point is never a good idea because sometimes your points may be crazy off. Like a point could be all the way over here, right? It could be, you could have two outliers as your first points, and then your line would be something like that. So you don't ever want to use your first and last points. You just want to use a line that is as close to as many points as possible. Okay? Moving on. So based on what we just discussed, I wouldn't change anything because I already knew this, but I would just keep my line how it was, which was probably like right around there. I've drawn it a lot of times now, and I know it's probably a little bit different each time, but I can see that it, hits some of the points, but not all of the points, but it's as close as it can be to most of the points. Okay? So just redraw it if you would like to here. And moving on. All right, here you are going to be answering this on your own. It says, deep water. Does the current in the water go faster or slower when the water is shallow? The data on the depth and velocity of the Columbia River at various locations in Washington State listed below can help you think about the answer. So when the water is shallow, so we're looking for small numbers here depth-wise. So this first one is pretty small because it's 0.7. This one's pretty small. This one's pretty small. This one's pretty small. It looks like these numbers are in order, which is nice. So the velocity is 1.55, 1.11, 1.4, 1.3. It's going down. So as these numbers go up, these numbers are going down. So basically, the more shallow the water, the faster. Okay? So that would be your prediction that you need to write down here. And if you were making a scatter plot of the data, what variable would you put on the horizontal axis, which is your x-axis? What do you guys think? So take a second to answer those, and then I'll show you what I would write here. All right, I would write that the more shallow the water, the faster the velocity of the current. And then our x-axis, remember when we have a table, we always put x over here, y over here, so our x-axis would be depth. Okay, moving on. All right, this is pretty much the same thing, but I want you to put it in your own words. How would you explain the relationship between velocity and depth of water? And then if the river is 2 feet deep, how fast do you think the current would be? I want you to make a prediction and explain why you chose that number. And we'll go over it in just a second. All right, so C is pretty much like the last question. Basically, the more shallow the water, the faster it flows. That's what velocity is, okay? And it says if the river is 2 feet deep at a certain spot, how fast do you think the water would go? Well, we have 2 feet right here. So, I mean, it's telling us exactly what the velocity would be. So it would be 1.11 feet per second. And we know this because it's right in our table, right there. Okay, moving on. All right, you can see here that they have taken that data that was in the table and they put it in a scatter plot. It says choose a data point on the scatter plot and describe what it means. And then it says based on the scatter plot, describe the velocity. I know it's just making you do this over and over and over again. I'm just going to choose this first point right here. And what this first point means is that at around what would this be? This would be what? 1, 2, 3. 1 foot. At 1 foot deep, the water flows 1.6 feet per second. Okay, you can choose any point you'd like and do the same thing. Based on the scatter plot, describe the relationship between velocity and depth. While looking at the scatter plot, you should be able to see that this is a linear trend, and it's negative, it's decreasing. This is a negative linear relationship. So as depth increases, velocity decreases. All right, make sure you have it down and we will move on. All right, consider these following questions. If you draw a line to represent the trend, would it make it easier to predict the velocity? I'm just going to answer this for you, yes, because you can use that line to make the prediction. That's the whole point of a line of best fit. And then it says draw a line that you think does a reasonable job. Okay? And use it to predict what the water will be when it's 8 feet deep. So go ahead and do this on your own, and then we'll check it in about 30 seconds. So draw a line of best fit and predict what the velocity is going to be at 8 feet. Okay, here is my line of best fit. I'm using that. I'm going to predict at 8 feet. So I go to my depth, go to my 8, draw a line up. See, it's around here. Draw a line across. I would say about 0.8, 0.7 maybe feet per second. You could have said anything within this range, and you would be accurate. Okay, moving on. All right, use your line of best fit to predict 8.6 feet. So 8.6 feet is, I think it's this line, or this dot that's actually right here, and your line of best fit is supposed to predict where that's going to be, but it should pretty much match up with where it shows, right? 8, this is 9, so it's like right in the middle here, and if you draw this across, it should be pretty close to where it actually hits. You don't need to write anything here. I just wanted to see if you need to check for yourself and see if it actually matches. If your prediction line matches the actual point that they give you, because they do actually have a point that's at 8.6 feet. Okay? And continuing. All right, and that is the end of our lesson for today. So basically, to summarize, when you're constructing a scatter plot, the variable that you want to predict, or the dependent variable, goes on the vertical axis, and the independent variable goes on the x-axis. You guys already know x and y. If you have an x, y table, x is always on your horizontal, y is on your vertical. Y is dependent on x. Okay. When the pattern in a scatter plot is approximately linear, a line can be used to show the relationship. That line is called a line of best fit, and you want to find a line which the points in the scatter plot tend to be the closest. That was our strategy. Okay, let's look at our exit ticket. All right, here's what you're going to have to do for your exit ticket today. You will have to choose a point on a scatter plot and explain what it means. We did this in our lesson. You'll have to use the line of best fit provided, so they're going to give you a line, to make a prediction. And you will have to share if you think the line of best fit that was drawn is good for the scatter plot. So you're going to have to look at it and be like, okay, was that a good line that they drew? Would I have drawn that same line? That kind of stuff. When you're done, do your reflection in Google Classroom, and then you can work on your weekly work or any missing work should you have not finished the work from yesterday. All right, we're done.